Okay, everybody, today I'm going to move along in the review videos here. It's going to be kind of a weird video. I might break it up into a few sections. Might break it up into two videos. I don't know. I'm on page 47 in the review book, Uniform Circular Motion, Centripetal Force, Universal Law of Gravitation, and Friction. Kind of a random sampling. Really, I think Friction ought to be back with some of the other stuff, but or maybe its own video. So we'll see what happens here. Let's start off with uniform circular motion, though. We did some experiments with this in class. I think we spun the rubber stopper. I don't remember. Anyhow, when something's moving in a circle, anytime something's moving in a circle, there must be a force moving in a circle. Now I'm kind of looking at it from a perspective view. I look at it from a top view, right? Anytime something's moving in a circle, right, it must have a force that is central acting. So here's the center of its circular orbit, let's say, right? There, by definition, must be a centripetal force acting to pull it in a circle. Now that centripetal force, it's not this is the velocity vector at a snapshot in time. That's constantly changing, right? That centripetal force is not some magical force that appears because something is moving in a circle. It's the force that is forcing the object to stay moving in a circle. So for instance, if we tie a ball to a string, and I think we did it where we passed it through that handle, right, and we hung some weights off the bottom, we spin it in a circle, it is a force of tension that moves the object in a circle. So centripetal force in this case would be force of tension. Other centripetal forces are normal forces, right? Normal force, which is a contact force from the ground. So for instance, if you're in one of those rides where, excuse me, if you're in a ride where you're getting spun in a circle and you stick to the wall, you know, it's hard to keep your arms out, but it's actually the force of the wall. It's a normal force that's forcing you in a circle. So like as you're flying around this thing, there's a normal force redirecting you. If there is no centripetal force, for instance, if you're riding this ride and the normal force disappears, you go flying off tangent. All right, you spin something in a circle, let it go, it flies off in a straight line initially, then it turns into a projectile motion problem. So the big point here is that anytime something's moving in a circle, doesn't matter what it is, anytime, there's always a central acting force, right, that we call centripetal. FC means centripetal force, and really this is a net force. This is a net force. All right, and this could be tension in a string. We'll see in a second. It could be gravity. For instance, if it's a planetary orbit, it could be gravity. Here it could be tension, gravity. It could be friction. If it's a car going around a racetrack, any number of other possibilities, a normal force, etc. It's just whatever force is acting in a circle. And we learned that the equation for the net centripetal force, so basically, you know, how big the force must be, right, is equal to mv squared over r. So the amount, I think of this as the amount of force required to move the mass in a circle with v and r, so to speak. It's like, here's the mass, right, moving in a circle. Here's the circle you want to move it in. Well, the amount of force required depends on how fast the object is moving and how much mass it is and the radius of the object. All right? the radius of the path. The shorter the radius, the harder it is to redirect this thing. So it takes more force. The bigger the mass, the harder it is to keep it moving in a circle. The harder it is to redirect its motion, because that's what's happening. This rope is constantly redirection. If this is a rope, the centripetal force is constantly redirecting this object's motion, right? It's constantly drawing it in towards the center of the circle. If the centripetal force disappeared, the object would just go flying off tangent to the circle. All right. We should note that we often call v squared over r the centripetal acceleration. You have to be careful there. Sometimes kids mess this up. Centripetal acceleration is just v squared over r. Centripetal force is mv squared over r. And your reference table is, a little bit mean about this. They give you AC equals v squared over r, and then I think below it they write, so they give you AC equals v squared over r. Oh no, they give you actually the force first. They say FC equals MAC, which makes sense. Force equals mass times acceleration. But then right below it, they say AC equals v squared over r. And really, we often just combine the two to say FC equals M times v squared over r. All right, so be careful about that. It's I'm not going to do an example of that right now. I'm going to move on to the gravity. Then I'll probably do a second video for friction. Maybe I'll tie the gravity and the centripetal force together. But the units are still newtons for centripetal force. The units for centripetal acceleration is v squared over r. And the big thing is that you just remember that these are not forces that magically appear. They're always a tangible force that exists because something is pulling an object in a circle, right? Oh, look at this. I just steel bearing, right? If I can get this to move in a circle, right? How do I get it to move in a circle? Well, I really can't, right? Unless I kind of constantly redirect it and try to push it from the outside in a circle. I can't really make it just magically move in a circle without pushing it towards the center of the circle. So it'd be a contact force causing that. But anyway, let's move on to gravity. There's some good questions in here in the review book, though. Actually, maybe I should look at a couple of those. Oh yeah, one of the classic ones is to give you a diagram and then say, okay, what's the direction of the velocity? Again, that's always tangent, and then the force and the acceleration, FC and AC, are always directed towards the center of the circle. And it's just different questions about how things change. And I encourage you to look. I have the review key to this review book posted online. So I encourage you to take a look at that if you want to dig into some of those questions. Now, gravity. All right. So the review book starts off with talking about universal law of gravitation, M1, M2. All right. We learned that the force of gravitational attraction between these, FG, of, we could say 1 on 2, or sorry, that would be 2 on 1 and 1 on 2, this force. They pull on each other, so this is representing the pull from mass 2 on mass 1. This is representing the force of mass 1 on mass 2. That's equal to magnitude to big G times M1 times M2 over R squared. R being the distance between their center of masses. And we did a little simulation lab on this. I think this is where we started doing some of our online learning here, right? In this unit, I think, is when we started. But we did a little simulation lab on this. That was fun. We saw as we increase the radius, the force goes down. As we increase the mass, the force goes up. It's just kind of a pain to plug this in. G is a constant found on the front of your reference table, 6.67. I often mess this one up, 10 to the negative 11. Newton times meter squared per kilogram squared. And then they're just kind of a big nasty calculation. Now, what does this have to do with this, where we said FG equals MG earlier in the year? Well, let's take a look. Let's take a look at the Earth. So here's the Earth. Here's an object on the surface of the Earth. All right. The radius of the distance between this object and the Earth is the radius of the Earth. We'll say that's the mass of the Earth, and the mass of this random object we'll just call little m. Well, the force of gravitational attraction between these two objects, which is equal and opposite, it's an action-reaction pair, is big G times the mass of the Earth times the mass of the little mass divided by the radius of the Earth squared. All right. Now, big G, ME, and radius of the Earth, those are all big constants, right? Those never change. If you're at the surface of the Earth, you're always this. And it turns out that if you plug in the mass of the Earth, the radius of the Earth, and big G in for that, you get 9.81 meters per second squared for all of this. Now, you should note that that value, right, and this is the mass of the object, that value is only good when you are 1 Earth radius away from the center of the Earth, meaning you're on the surface of the Earth. So that's kind of a cool little thing. So if you go up here in outer space, you're now 2 Earth radii. G is not 9.8. It turns out it's a quarter of what it would be because you're doubling the radius, and then that is squared. So it ends up being 1/4 of 9.81. If you triple the Earth radius, which is off the board here, I could do it down here actually. If you go 3 Earth radii away, it would be 1/9 of the amount of gravity acting on you. So it changes by r squared. That's one of the common types of questions. Like if you increase your radius, by what factor does the force of gravity change? Well, it changes by whatever it is squared. It goes down as it gets bigger. All right, so that's it for now. Video's about to cut out. It's friction, or I'll do another video for friction.